I'm Dr. Ron England, and today I'm coming to you with COP 3530 data structures, and our topic for today is recursion. So what we really want to learn about recursion is to understand what it is. Recursion is not a tremendously complex topic but sometimes it's hard to wrap your brain around it. So what we're going to do is we're going to look at the definitions of what is a recursive definition and what's an anchor. We also call an anchor a ground case. We need to be able to look at recursive equations and interpret them. We also need to be able to code recursive equations. We actually need to write code to implement them. And we also need to understand, and in many cases, be able to implement iterative solutions that don't use recursion for the same types of problems. These can get tremendously complex. Things that really are simple to do with recursion can be amazingly difficult to do iteratively, but for every recursive solution, there is an iterative solution. So let's first look at what we mean by recursion. And this, right off the bat, is going to seem counterintuitive. A recursive definition is something that uses the thing that you're defining in the definition. So what would this actually mean? Well, it's like saying that the definition of a double dog dare is 2 dog dares. Well, if you don't know what a dog dare is, then how can you actually know what a double dog dare is? I use the definition of the piece of the dog dare it's like, how does that work? Well, the truth of the matter is, in the world of mathematics and computer science, this can work. So what we're going to do is let's look at just a simple something that is a mathematically recursive definition. So this definition is actually the definition of factorial. Okay, this is the factorial definition. But what I'm saying here is that the function of n, well, if n is equal to 1, n is 0. Okay, no problem. However, if n is anything greater than 0, then it's equal to n times the function of n minus 1. Well, how can that work? Because the function of n is the thing you're being defined, and in the definition is f of n minus 1. Well, if you think about this, this is a factorial. What do we mean by that? Well, let's think about this definition and let's use it. So if I were trying to do 6 factorial, well, if you know your mathematics, you know that 6 factorial is 6 times 5 times 4 times 3 times 2. You don't need to do times 1 because it really doesn't matter. Okay, because times 1 is always times 1. But 6 factorial is equal to 6 times 5 factorial. So in other words, the function of n, the 6 factorial, is equal to 6 times the function of n minus 1. Okay, or 6 minus 1. So in this case, it's a workable definition. We can use this definition to figure out the solutions to the factorial. So we have defined the factorial function in terms of itself, meaning that it is a recursive definition. Now, how will we implement this in code? Well, here's a little bit of JavaScript code. This really isn't that hard to do. So if n is 0, you come back with a 1. Otherwise, you return n times factorial of n minus 1. Well, factorial is the name of the function, so you're calling the function from within the function. We don't care how this actually gets executed inside the computer. Probably going to be using a stack, and the stack call is going to call itself, and there's a set of code that actually executes. But it's a simple solution to solving the factorial. It's not that hard to do at all. So we can write these types of functions in terms of themselves, and that is your recursive definition. The ground case, the anchor, which you always have to have if you're doing a recursive function, is that case which escapes you from the recursive call. If you never escape from the recursive call, the function's going to go into an endless loop and never end. So you have to have some case that grounds it and moves it out. Well, in this case, it's if the n is equal to 0, you simply return a 1. You don't call itself. Otherwise, it's always going to go back and return n times factorial of n minus 1, which means that it's always going to call itself. Okay, so that's that anchor, that's that ground case. And remember, if you do not have a ground case, or you don't get to the anchor of the ground case, guess what? If you never execute that piece of code, you're going to go on forever. And what it's going to look like to you is that the computer just locked up. So if a function calls itself, it somehow has to get out of that call. So remember, when you're writing that recursive function, if you don't have that ground case, bad things are going to happen. So let's look at another example. I like the one example of factorial is really straightforward. But we can look at the example of, let's say, 2 to the nth power. It can really easily be written recursively. So what do? Well, in this case, here's your basic function. 2 times f of n minus 1, if n is greater than 0, that is going to be able to run itself again recursively, and you're going to basically get 2, 4, 8, 16, 32, 2 to the n power for every value of n. But because you know that 16 is actually equal to 8 times 2, but 8 times 2 is the next one in the recursive thing, you can see it's not that hard to figure out mathematically. Relatively simple examples definitely gets the concept of how the recursion works. And again, in this case, and I actually do have a mistake here I want to point out here, is that I said return y times power of base of n minus 1 in the code. It's actually return base times power of base of n minus 1 for that. So there is no y. If you actually wrote this piece of code, you would be going, oh my gosh, it just told me that this variable y is not defined. Well, because it's not. You should be able to spot things like that, though, when you're actually writing the code. But you can see that this function is a really straightforward and easy function to write, to define. And in this case, it's not just 2 to the n. I can do this for any base. I could have just made base equal to 2 automatically, and it would only have done powers of 2. But I can actually make this work for any kind of base. So, some different methods of recursion. The basic recursive method that I just showed you is the simplest form of a recursive call, which is called tail recursion. The end of the function calls, you make that recursive call at the end of all the other options. So essentially, you've got the ground anchor case, which you check for. If it doesn't exist, you go into the recursive call. Power, factorial, both examples of tail recursion. But it's not the only recursive type of method that you can do. So you can have things like non-tail recursion. One of the classic cases of recursion to solve a complex problem is the Tower of Hanoi problem. And if you're in COP 3530 or you're in any algorithms class, you're going to see the Tower of Hanoi problem. It's a classic problem that's solved recursive calls. It's also used to demonstrate why algorithmic complexity is extremely important, because the solution can blow up very fast for large situations of n. But if you notice, you have an anchor case here in the function call, then you've got a recursive call, then you've got a call to move, and the call to move there, I haven't written the move function because I really don't need to, but what move would do, from, to, and via would be stacks. Okay, a simple stack, and move would take one block off of from and move it on to 2. Okay, so that's, pop off of from, push on to 2. Okay, that's it. Then it calls Hanoi again. Notice that the order of the execution calls changed. But this is an example of a non-tail recursion. It actually has a recursive call that actually occurs after some of the things some of the movements are made. So you have now the basic tail recursion and non-tail recursion that you can know about. All really tremendously straightforward. I hope that you kind of get this concept. One thing to point out in the Tower of Hanoi call. If you look at the function Tower of Hanoi and you look at the function definition, n, from, to, via, okay, the order that they come in. In the first recursive call, you call it n minus 1 from, via, to. What you're doing is when you flip the via and the to in the function call, they come back over, and now they're actually back to being 2 and via, but the stack gets moved over. They get flipped. So the recursive call, instead of saying, okay, now move this block from here to here, and this block from here to here, and this block from here to here, what you're doing is you're always moving this block to this block. every single time. There's only one move call from the two. What you're doing is you're taking the actual stacks. If you visualize the stacks as 1, 2, 3 in the Tower of Hanoi, the stacks are then just switched. The move is always the same, from to two. Just pointing that out for those people who have worked with the Tower of Hanoi, or, but also noting that if I can change the order of the calls that they're being called and make it have a completely different action. Now, there's one more type of recursion that we're going to look at here, and we're not going to spend a tremendous amount of time on it because it's pretty easy. But the recursive calls that we've shown you were straightforward. The function called itself. But you can have indirect recursion. You can have a function that calls another function that calls the original function. And that's called indirect recursion, and that will still work. You can still have f of x called g of x and g of x called f of x. Okay, and you can actually have f of x called g of x, which calls h of x, which calls f of x. Okay, those are all examples of indirect recursion. One last thing to note with recursion is that every recursive function also has an iterative solution. What I mean by an iterative solution is a solution that does not rely on recursion. We are not going to go into the depths of figuring out the iterative solutions except for the very, very basic recursive functions. The beauty of recursion is it allows you to define the actual parameters of a solution in simpler terms. If it doesn't allow you to define the solution in simpler terms, then the indirect solution is going to probably be the better solution anyway. And in many cases, this indirect solution is a leaner solution. It's either faster, less complexity. However, iterative solutions do exist for all those. And if performance is an issue, it's good at looking at the performance of the iterative solution versus the recursive solution. So hopefully what we've done here is you now understand what we mean when we say recursion, what a recursive definition is, what the ground and anchor case is, that you can actually look at a recursive function, figure out what it means, code it, put it in a computer code, and know that there is at least an iterative solution that's available for all the different recursive all the different recursive solutions that you can come up with. So this is a great topic. It's one of the most used topics in computer science and IT, and one that you definitely need to know. I'm Dr. Ron England, signing out from Daytona State College.